call integration by parts, right? So in many cases, we're not going to be able to identify our functions or the integrand in the structure of these immediate integrals that we saw in the last video, right? And so for those cases, you will need more techniques, right? And so in this video and the next ones, we're going to see how to deal with this. One of the first techniques that we want to learn and we be able to use is what we call integration by parts. Okay, and that means dividing our function, whatever is our integrum. This is normally you will see it like this, right? The primitive of some function h. So we have to be able to separate it into two parts, right? One function f and one function g, which we identify as the derivative of another function. So g prime is another function g, right? If we can do that, then it's guaranteed that this primitive is going to be equal to this, right? And the proof is easy, right? So the proof for this, it just follows from the derivative, the rule of the derivative, right? So we have that the derivative of f times g, right? Let's say a primitive for this, right? A primitive for this is going to be f times g, right? Primitive of the derivative of this. But the derivative of this we can compute using this, the product rule. So this is the product of f times g prime, and then plus the primitive of f prime times g, right? And we can separate these two primitives because we know that this operation is linear, right? Now you just need to solve for this, so take that subtracting to the other side and you get the original formula. Okay, now I guess most of you guys, if you have seen this before, typically you will have seen this like this. The primitive of u times dv, where dv is this, okay, this is what we call dv, is u times v minus the integral of v du, right? And there's some, a lot of mnemotechnic rules to remember this, right? So is this the same as identifying our function u and our function dv, which is g prime dx, and then be able to compute the derivative of f and the primitive of g, right? And so then you have to compute this like this, okay? So a very classical example of this, the application of this formula is to compute the primitive of this, right? So typically, whenever we have an exponential, we want to use this as our g prime or dv if you want, right? And u is going to be x, right? So du is going to be the x, and v is going to be, so this is dx, okay? Using the notation that most of you will have seen, right? In other words, what you can say is that g prime is going to be e to the x, f is going to be x, and then applying the formula, then you have x times e to the x minus the derivative of x, which is 1 times e to the x dx, and the primitive of this is e to the x, so you have e to the x minus e to the x, or in other words, x minus 1 times e to the x, right? That's the primitive, plus c, okay, plus a constant. Okay, so either way it works. If you already know how to do it using this notation, then go ahead, just as long as you know what you're doing. If not, you can do it using this notation, okay? Both ways are fine. Okay, so this is useful whenever we have, for instance, a polynomial, right? And that's multiplying, for instance, an exponential or a cosine or sine, things like that, right? So which is easy to integrate several times to find a primitive, and the polynomial is easy to differentiate, and if you do it over and over again, it will disappear, right? So the functions that you have to find the primitive of in this part get simpler and simpler, right? And so you just need to apply this formula over and over again, right? As many times as you need. Okay, so well, using this knowledge, I gave you this exercise to do on your own. X squared plus 1 times the sine of 2x minus 1. Okay, and then let's see, we can, let me go back here. We can actually use this trick to compute, for instance, the primitive of the logarithm, right? So now here, what's the problem? Well, we can see how can we find this as an integration by parts, right? Now, it's clearly f is clearly going to be the logarithm of x, because we don't know the primitive of this, but we know how to differentiate it. But then g prime is, and this is a trick, this is equal to 1. Okay, so then the integral of this is going to be the logarithm of x minus, and then you have the primitive of 1, which is x, one of the primitives, times the derivative of the logarithm, which is x. So this is the primitive of 1, so this is just the logarithm of x. So this is x, sorry, because this is times g, not times f, right? X times the logarithm of x minus x plus c, or in other words, x times the logarithm of x minus 1 plus c. This is the primitive of the logarithm. Okay, so again, if you don't remember this, at least remember how to get it easily using integration by parts, right? We can generalize this argument that we have just done for the logarithm to obtain the primitive of the logarithm, to obtain the general primitive of any inverse. Okay, so if we have a function f, right, and we know that f, capital F, is a primitive of f, right? Now, the primitive of the inverse, using the same technique, using integration by parts, we get x times f minus 1, okay, just like in the logarithm, minus, and then we have x times the derivative of the inverse, right? Just like what we have done with the logarithm, right? Now, x, because of the properties of the inverse, is just f at f minus 1, right? Because the composition of f at its inverse is equal to x. So this is equal to f times the inverse minus, and then let's say this is f at f minus 1. Wait a minute. Maybe it's easier to rewrite. We have f at f minus 1, right, instead of x, and then we have f prime, and sorry, not f prime, the derivative of the inverse, prime at x dx, right? But now you can see how this works, right? This is the derivative of this primitive, right, evaluated at f, times the derivative of the argument, right? So you can see the chain rule, right, that this thing, how to say, that if we have the primitive of the inverse evaluated at the inverse, right, we're gonna have f evaluated at the inverse, and as we have done with the other immediate integrals or primitives, then we have to multiply by the derivative of the argument, right? So this thing is the primitive of the inverse, sorry, the primitive of f evaluated at the inverse, right? So now we can write this as a theorem, right? So if we have a function f with an inverse f minus 1 and f prime is small f, then we have this, that the inverse of f, the primitive of f minus 1 is x times f minus 1 minus capital F, which is the primitive of f, the original function, I evaluated at f minus 1, right? So let's use this formula to find the primitive of the arctangent, right? So then we have x times the arctangent, and then we need the primitive of the inverse, right? So here we have f is going to be the tangent, and the inverse is going to be the arctangent. So we need the capital F, which is the primitive of the tangent, right? But the primitive of the tangent we've seen is the logarithm of the absolute value of x, right? So this is going to be minus the logarithm. Instead of the cosine of x, it's going to be the cosine of the arctangent plus c, right? And now we need to simplify this expression, right? So how do we do that? Well, we need to rewrite the cosine in terms of the tangent, and the easiest way is to realize that the cosine squared, or 1 over the cosine squared, is equal to 1 plus the tangent squared, or that equivalent, sorry, that so the cosine squared of x is equal to 1 over 1 plus the tangent of squared, right? And that's easy to see if you compute it's in the other way around, right? You have 1 over the cosine squared, right? This is, if you evaluate this is the sine squared divided by cosine squared, then this is cosine squared divided by cosine, sine squared plus cosine squared equals 1, right? And then you solve for the cosine, you get that, right? So then the cosine is just the square root of 1 divided by 1 plus the tangent squared. So the logarithm of the cosine of the arctangent, right, is going to be the logarithm of the square root of 1 over 1 plus the tangent square of the arctangent of x. So you have, so let me see, if instead of having this we have the cosine of the arctangent, here we have the arctangent, so that's x squared. We have done this before, right? So then we have, this is the logarithm of the square root, well, we have the logarithm of 1, which is 0, minus the logarithm of the square root of 1 plus x squared, right? But minus minus is plus, right? So you have plus the logarithm of the square root of n 1 plus x squared, and, or in other words, we have 1/2 outside the logarithm of 1 plus x squared plus c. That is the inverse, sorry, the primitive of the arctangent. Okay. Now with this, having done this with this information, you can try and find or prove that the primitive of the arcsine is going to be like this: x times the arcsine of x plus the square root of 1 minus x squared plus c. Okay. And in some cases, okay, just by, in order to finish some of the integration by parts, we can, how to say this, we will be able to get the same integral formula after we apply our integration by parts formula, and then so you can solve for this original integral by subtraction. Okay, it's easier to see if I give you an example, right? So this is the logarithm of x divided by x, right? And so here it's easy to see that our function g prime is going to be 1 over x, and our function f is going to be the logarithm, right? Now the primitive of g, or one of the primitives, is the logarithm of x, and here the derivative of this is going to be 1 over x, right? Now so this is f times g, the logarithm of x squared, minus, and then we have, you see, the logarithm of x divided by x divided dx. So this is the same as before, so we can take this summing here, so 2 times this is equal this, and then divide by 1/2, and so now you get this solution plus c, sorry. Okay, you see how this works, right? This is very typical. This appears a lot in trigonometric integrals, right? So for instance, e to the x sine of x dx, right? And let's call this integral s, and then we have the integral, the same integral with the cosine, right? Now let's see, this is going to be where in this case it doesn't matter if we choose one or the other, right? So let's use this as g prime. So we have to find the primitive of this, so this is minus ex cosine of x plus, and then we have ex cosine of x, because then the derivative of e to the x is the same, right? So we have s is this plus let's call this c. Okay, we know this is c, And then here we have the primitive of this cosine is the sine, and then we have minus the integral or the primitive of this, right? But this is what we call s, right? So we have a system of linear equations, right, with two variables. So let's see. We can substitute here, right? The second in the first formula. So we have e to the x cosine of x plus, and then we have e to the x sine of x minus s. We take this sum in here, 2s, and then divide everything by 2. So all of this divided by 2. So this is e to the x divided by 2 sine of x minus the cosine of x. This is the first integral. And then the second one is the same. C is e x sine of x, and then minus s with its minus e to the x halves. So this is e to the x halves plus sine of x plus the cosine of x. This is what you get. And then, okay, plus c and plus c. Okay, don't remember to write your constants. Don't be like me. Okay, it's important, this constant, because depends on many many properties of the original function it's going to be important later on. Okay, so these two, again, these are easy to get if you are you may want maybe to remember them, but really it's super easy to get them in less than 5 minutes. Okay, and so you can use this thing to get in a sense to find recurrence formulas to these integrals. Okay, so what I mean by this is that sometimes you get, for instance, a primitive like this, right? This is the integral of 1 plus x squared to the n, right? Now if n is equal to 1, this is kind of a sequence, if you want, of primitives, right? One value per n, right? If n is equal to 1, then this I1 is the arctangent, right? Plus c, okay? Well, but we can remove the constant here. We don't really want to care too much about the constant. Well, we can talk. It's okay. Okay. Now the question is, how do we find the recurrence formula for this? Because so think about it. If this is n equals 2, then this is already hard to compute, right? If n is equal to 3, it's harder. So, right. So if there's a way that we can compute in as a function of in minus 1, then because we know I1, we can compute I2. With I2, we can compute I3, and so on. Okay. So how do we see this? Well, we can apply integration by parts to this, right? So this is the integral of 1, or the primitive of 1 plus x squared divided, to the n plus 1. And then we have to find the primitive of this using integration by parts, right? And so, well, before doing that, okay, what's easy to see is that we can write the numerator as this 1 plus x squared minus x squared, right? This is 1, we're just summing and subtracting 1 plus x squared, right? And this is the x. So we can now separate this part, and this is 1 plus x squared divided by 1. This is just 1 over 1 plus x squared to the n dx, but this is just our integral with index n, and then we have minus x squared divided by 1 plus x squared to the n plus 1 dx, right? And now we can integrate this thing by parts. Okay, and now we have what? We're gonna find, wait a minute, in order to, let's say, how to say this, we want to be able to find so we want to be able to integrate this, right? So this is going to be 1 plus x squared to the minus n minus 1, right? This is what it is. So in order to integrate this and get 1 plus x squared to the minus n divided by whatever, right, we need to get in the numerator something that's the derivative of this, and this is equal to 2x, right? Now here we have an x squared, so this is equal to x divided by 2, right? You see, x squared 2 divided by 2, right? And now we have that the function, this is x times the integral of this, so let's say first, so this is 1/2 of, and then we have x times the integral of this, so this is 1 plus 1 over 1 plus x squared to the n, and then divided by minus n, so minus n here, right? You can do it on your own if you want, and then plus 1 over n times the integral of this 1 over 1 plus x squared to the n, and the derivative of x, which is 1, right? dx. But then again, this is in, right? So this is 1/2 of in divided by n, right? Minus, and then we have x divided by n 1 plus x squared to the n. Right, now we can make this, find this together. So we have that in plus 1x is in, right? And then, sorry, this is in of x, and then minus 1/2 of in over n, so minus 1 over 2n in x. So let me rewrite this. This is 1 minus 1 over 2n times in x, and then plus minus plus x divided by 2n 1 plus x squared to the n, right? You can get this formula. Okay, so now let me erase this part. Now having that, we can now find all the values that we want of this integral by just substituting here. So we have n equals 2, then this is I2 is just 1 minus 1 over 2, so 1/2 of this, which is the arctangent. Well, this is obviously plus c. Well, not, you don't really, yeah, the plus c is here already, sorry. So plus, and then we have x divided by 2 times 1 plus x squared, okay, and then plus c, right? Now if n equals 3, this is I3, which is 1 minus 1 over, in this case, well, sorry, this is n equals 2, right, for this formula to occur. So this is n equals 2 minus 1 minus 1/4, 3/4 of this, right? So let's call this I2. Let's not substitute. And then we have plus x divided by 4 times 1 plus x squared plus c, right? And then you can input here this thing here, okay? So you see how this works. We now have a formula for this integral, or this primitive, as a function of n without having to compute more primitives, okay? And that's kind of the power of the integration by parts.